as well.
My dad wanted Adam to change his last name.
There's a reasonable case to be made. Burton.
That was great. And of course, Adam doesn't care either way. He's just too laid back to things bother him. Leave a lot of water.
And a ton of water, yeah. The cups have a little bit of a problem there.
You know what it was? It was the bottom of these things was like
Was
bowed.
wilting or-
Yeah, so they weren't standing up straight. Yeah.
In the early morning, I'm not guaranteed to see that. Well, thank you very much for.
Yeah, thank you so much for doing this. I'm glad it worked out with the paper and everything.
Yeah.
Yeah, with nature, so that was good. Have you already gotten requests from reporters? Or?
Yeah, just 3 or 4, so
good.
a few bites. We'll see how we go.
Yeah, good, great. All right, I'm going to get started. Hi. Oh, you ready? This on? All right, hello. Welcome to our first press conference of the 2016 AGU Fall Meeting, attributing mountain glacier retreat to climate change. There is also a paper that was published today in Nature Geoscience, and there are some copies in the back. Our participants today are Gerard Rowe at the University of Washington in Seattle, Summer Rupert from the University of Utah in Salt Lake City, and Ben Pelto from the University of Northern British Columbia in Prince George, British Columbia. Thank you.
Thank you for coming. And as Nancy mentioned, I'm going to make a short presentation on work that was just published, I think about 2 minutes ago in Nature Geosciences, and also work that I'll be presenting on Friday. And I want to acknowledge my co-authors, Professor Marcia Baker at the University of Washington and Florian Hurler at the University of Innsbruck. The bottom line of this work is quite simple, that the worldwide retreat of glaciers is categorical evidence of century-scale climate change that is global in scale. So we're all very familiar with this. Images of glacier retreats are prominent in the public perception of climate change, and that is backed up by data. The World Glacier Monitoring Service has 227 glaciers that have observations which span the 20th century, and 226 of those they report as retreating. So why isn't this obvious then? Glaciers are complicated. They respond to climate over the course of maybe a few decades. It's possible their retreat is a recovery from the Little Ice Age, or maybe glaciers are simply noisy and they have large fluctuations even in a constant climate. So in part because of this, the last round of the Intergovernmental Panel on Climate Change was actually a little bit tentative. Their conclusions are that only it is likely, which in their language means a 2/3 chance, that a substantial part of glacier mass loss is due to human influence. Not really clear what substantial means, right? So let's look at a general climate record. This happens to be summertime temperatures in Austria between 1880 and 2010. And if you look at that, I think you'll believe me that the temperatures are rising, and in fact they are, by about 1.5 degrees centigrade. But what your eye also sees is a great deal of year-to-year variability or natural fluctuations. And you can characterize any climate record in terms of what's called a signal-to-noise ratio. And that's a very simple ratio, which is the magnitude of the change divided by the magnitude of the variability. Happens to be about 2 in this case, but whenever you're dealing with detecting a climate change signal, it's a key question to ask how large is the change we've observed relative to the variability that would happen if there were no climate change. We can use mathematical models of how glaciers respond to climate to illustrate the principles involved. The top 2 panels here are 500 years worth of random accumulation and melt season temperature fluctuations, such as would occur every year just simply due to the vagaries of the weather. And this lower panel is a mathematical model of a typical glacier response to those random fluctuations. Weather is noisy, so climate is noisy, so the glaciers will also fluctuate, in this case by maybe plus or minus half a kilometer, more slowly than the climate, but still fluctuating. Now let's put a 1.5 degrees centigrade trend at the end of that last 130 years of the temperature over there. You can barely see it really in the top right panel. You look at what happens to the glacier basically falls off a cliff. And the reason for this is that a glacier acts as a filter of the climate forcing and actually amplifies the signal of change. So the glacier retreat represents a purer signal of climate change than the local thermometers do themselves. This is a signal-to-noise ratio of 10. Now, it turns out we actually have pretty good observations, instrumental observations with thermometers and rain gauges for the last century or so, and we have, in many places, good observations of the magnitude of the glacier retreat. So what we can do is use the mathematical analysis that I've represented graphically in these slides and reverse engineer what we expect the glacier variability, the natural glacier variability to be in a constant climate. And when we do that, we can make probability distributions. These are probability distributions for 7 widely dispersed glaciers from the Alps to Scandinavia, North America, Asia, New Zealand, Argentina. And these represent the probability that in any 130-year period, we would see a retreat of the given magnitude. What you'll see is each of these glaciers, they have a very different width because each glacier has a unique geometry and climatic setting. But what they all share in common is that when you plot the observed retreat onto these probability distributions, they all lie in the very far wings of the distribution, meaning it is very unlikely that this could have happened in a constant climate. We've done this for 37 glaciers around the world, and for most of them, in IPCC language, it comes back as virtually certain. That is, there is a greater than 99% chance that the retreat required a climate change. For all but one, it's either extremely likely or very likely, and even for the least significant, there's still an 89% chance that it requires a climate change. So, to recap, the worldwide retreat of glaciers during the industrial era necessarily requires a climate change, and it needs to be centennial in duration and global in scale. Well, is it due to human influence? The glaciers don't know why their climate's changing, right? They only know that the climate is changing. So this fits into a larger body of work, and drawing on other studies, the IPCC concludes it is very likely that most of the observed change is due to human influence. Most is also a little bit of a weasel word, but in my opinion, most should mean between 80 and 120%. Why care? Well, hopefully this is an upgrade in our scientific understanding of the relationship between climate change and glacier retreat. And perhaps a little bit more philosophically, it's important that we have things that we can look at on the landscape and have an appreciation and intuition about what climate change means. And glaciers do very much represent that with this strengthened connection. And then perhaps they also provide a somewhat sobering perspective on how far out of equilibrium these natural systems are. Okay, thank you. I'll hand over to Summer.
All right, thank you for this opportunity. And I'm going to focus in from the global scale on high mountain Asia. High mountain Asia is has the largest source of snow and ice outside of the polar regions compared to anywhere else on the planet. And it also has billions of people downstream of these glaciers and snow and ice. And this has given rise to a nickname for the Himalayas, the water towers of Asia. And there are several key questions with this. The first is, how much are these glaciers changing? Right? What is the impact of climate change over recent decades on these glaciers in high mountain Asia? And what does this mean for things like global sea level rise and water resources for downstream populations? This image in the background has become a fairly iconic image from NASA that really highlights some of the issues with trying to understand and quantify these changes in high mountain Asia. These glaciers straddle the disputed border of Bhutan to the south and China to the north. And what they really do is exemplify the complexity in the region, from very large, tens of kilometers glaciers right next to really small glaciers throughout the regions. And there's tens of thousands of these. In addition, some of these have shown really drastic retreat over recent decades and over the last century. And these are mainly the clean ice glaciers here. But to the south, there are these debris-covered glaciers. That just means they have a lot of rock and sediment ladling these glaciers. And if you look at area changes, a lot of these show no discernible change in area or very little change compared to the clean ice glaciers. There are also these glaciers, many glaciers that terminate in glacial lakes. So just like tidewater glaciers, the lake water thermally undercuts the ice and causes the ice to calve off, adding this mass balance or this mass loss term for these calving glaciers. And these have very large retreat. So some of the questions in the region are, these debris-covered glaciers in some areas are more than 30% of the glaciarized area. Yet they don't show, from an area perspective, much change. Is this because as the debris gets thick, it insulates the glacier ice and makes them less sensitive to changes in climate? Or are we missing something? The calving glaciers are retreating and thinning rapidly, but they tend to be a very small percentage of the glaciarized area. So there are a lot of questions about whether or not these actually matter that much in terms of the regional balance of these glaciers. So they haven't received quite as much attention. So what we really need in this region of high mountain Asia is a regional perspective of glacier changes over multiple decades that coincides with recent changes in climate. To do this, one of my former graduate students, automated a pipeline for tapping into historic spy satellite imagery to detect changes in these glaciers over multiple decades. On the left here is the Hexagon satellite, which was originally put in orbit for a decade and a half or more to peer over the Iron Curtain. And it took global images that covered the entire globe in stereo, so you could get terrain images or terrain models from those stereo images. These film capsules were ejected in the upper atmosphere, and spy planes would swoop by with grappling hooks and snatch them out of the atmosphere, and then develop those images to look at what was going on in other parts of the planet. What we did was take those stereo images and turn them into terrain models. So on the top is the Hexagon image from 1975 of the Himalayas, and an Aster image from 2007. If we subtract these two images, we can look at the changes in glaciers that have occurred over this almost 40-year time span. And here's the results centering again on this border of Bhutan and China. Blue dots are clean ice glaciers. Black dots are those debris-covered or sediment-covered glaciers. And red are the lake terminating or calving glaciers. And the size of those dots scale with the size of the glacier. The graph on the bottom, that red bar, is 0. So if any of these plot at 0, they're healthy. They're not going to change size. If they're positive, they need to grow. If they're negative, they will continue to shrink and they're in a deficit, right? And as you can see here, all of them are negative, including the debris-covered glaciers. And in fact, there's no difference statistically in the mass loss over the last almost 40 years for those debris-covered glaciers than there is for the clean ice glaciers. So climate is no respecter of glacier type, right? Whether they're debris-covered or calving or clean ice, if the climate warms, these glaciers retreat or shrink in size. If the climate cools, they'll respond. But what we also see is that these calving glaciers, even though they're a small percentage of the area, they're a disproportionate amount of the mass loss. So they tend to cluster at much more negative values. So in this particular regions, these glaciers are less than 20% of the glaciarized area, but they're more than 30% of the mass loss. So these glaciers need to be a focus coming up if we're going to understand mass loss over time in the Himalayan region. So we know that glaciers have been thinning, retreating, shrinking in the Himalayas over the last at least 40 years. And we know that they're sensitive to changes in climate, so they'll continue to change under future climate scenarios. But the question is, what does this mean potentially for glacier contributions to water resources in coming decades? So this next image zooms out a little bit into the broader Himalaya, Hindu Kush, Karakoram region and shows the 3 different major watersheds feeding the billions of people living downstream of these glaciers. So the yellow outlines are the individual watersheds. The dark blue rivers are shown for each one. And then the light blue are the glaciarized regions feeding those rivers. So while we know that as climate continues to warm, these glaciers will continue to shrink. All our numerical models, mathematical models show this. It isn't obvious what this means for water resources. In particular, as glaciers shrink in area, there's less area over which melt to happen. So that would decrease the amount of water feeding these rivers. But as temperatures warm, the melt rate goes up. This would increase the water feeding the rivers. So the question is, which one wins in terms of water resources? So this image here is just showing the change in glacier discharge. This isn't the change in the Indus River discharge or amount of water flowing through in a year. It's just the glacier contribution to it. The blue line is the Indus from 2014 to 2100, and it shows mostly a decrease in the percent of glacier contribution to water resources in coming decades, and by 2100, a decrease of over 40% in glacier contributions. But if we move to the Brahmaputra, or to the Ganges, just a little bit to the east, we actually see it increases for a little more than a decade and then drops off, but the net decrease by 2100 is only about 5%. So not a huge change in the Ganges according to this particular model. Whereas the Brahmaputra has a very different signal. So even though glaciers are losing volume rapidly in this region, you have a large, more than 40% increase in glacier contribution to meltwater flux in the coming decades, and then drops off drastically to a more than 60% total decrease by 2100. There's huge uncertainties, of course, in each of these numbers, but the general relative pattern and differences between the watersheds holds true. But the question here is, how do we then decrease those uncertainties? When you have tens of thousands of glaciers across really complex terrain and complex political situations, how do we work in this region? Well, it turns out that the vast majority of these glaciers are really, really small. But less than 10%, the largest glaciers, contribute more than 75% of this meltwater discharge. This reduces the number that we need to focus on dramatically to a much more manageable size in a way in which we can actually improve the certainties here. So in summary, Josh has created a new automated pipeline for processing declassified spy satellite imagery that allows us to see much more detail in glacier changes in this region. What we find out is that climate change really is no respecter of glacier type. Debris-covered calving, clean ice are all thinning and retreating in response to recent warming, but the calving glaciers are more important than we thought. They are disproportionately draining the Himalayas. Finally, climate change will shrink water reservoirs, the ice reservoir within the Asian water tables into the future, but the impact of this on water resources is not necessarily a steady decline. It takes on different patterns depending on the distribution of glaciers over space and time. And finally, turns out size does matter. Largest glaciers tend to dominate the meltwater resources in this region. I'll turn it over to Ben.
Hi, so my name is Ben Pelto. I'm a PhD student at the University of Northern British Columbia, and I've spent the last 12 years working on glacier change studies across Western North America as well as on Mount Kilimanjaro, and those opportunities have given me a chance to witness the impacts of climate change on glaciers across many different regions. So today I'm going to talk to you about advances in glacier mass balance studies, and I think the best place to start is just by talking about what glacier mass balance exactly is. So glacier mass balance is essentially glacier health. It's really a measure of how much a glacier is gaining or losing over a given time period in terms of mass. So if we take the amount of snow that falls, which is accumulation during the winter, and we take the amount of melt that happens during the summer, the sum of those terms gives us mass balance. Usually we like to think of mass balance as something, maybe annual mass balance or decadal mass balance. So if we're in a given year where we had more snowfall than melt, we're going to have positive mass balance. If we're in a year where we had more melt than snow fell during the winter, we'll have a negative mass balance. So glacier mass balance is a logistically difficult thing to undertake. It's quite fun, I assure you, but it's a series of simple measurements that I'm going to walk you through here that we typically take. One is simply snow depth. Another is snow density. So we dig snow pits or take snow cores in order to get the density, and the combination of depth and density gives us how much water is contained within the given snowpack. We also need to know how much melt is occurring. And so to do so, we usually drill ablation stakes or long poles drilled into the ice. So shown on my side here in this image is an ablation stake sticking out about 3 meters out of the ice. So that stake had been flushed with the ice the previous year. So it's about a basketball hoop of melt at that particular location over 2016. And 2016 was a fairly mellow melt year, especially in comparison to 2015. So that's how we measure melt on bare ice. Global glacier mass balance studies are shown on this map here. So the World Glacier Monitoring Service has a little under 100 glaciers around the globe that are reporting annually measurements of mass balance. And 37 of those are long-term records as shown with the red squares. So we'll be looking at the data from those glaciers on the next slide. So here we have average mass balance of global glaciers. So it's that selection that I just showed you on the last graph. And what we see here is that we've had, over the globe, we've had average mass loss for 35 consecutive years. And you can also see the dashed lines on here are decadal averages. And you can see that with each decade, we've had a greater rate of mass loss as we've moved to present day. My father, Maury Pelto, also studies glaciers, and he recently published a book on climate change impacts on mountain glaciers and looked at 165 glaciers across 10 alpine regions over the last 30 years, and 162 of those 165 glaciers had retreated significantly, that is, shrunk in size significantly. The World Glacier Monitoring Service reports that average mass balance over the first decade of the 21st century was just over half a meter water equivalent. So that's the equivalent of taking about a 20-foot thick slice off every glacier around the world. And keep in mind that's an average, so some glaciers haven't lost that much, some have lost a lot more. But just every glacier on average, that's how much ice was lost just in the first decade of the 21st century. So as you saw, particularly in Summer's talk, remote sensing has really revolutionized the way we're able to observe and study glaciers. You can see from the methods I showed you early on that physically working on the glaciers is difficult, and there's only 100 around the world that are reporting annual mass balance. So now we know that there's about 200,000 glaciers in the world, and we're studying for mass balance around 100 of them. You suddenly realize that's a pretty small sample size. And these 200,000 glaciers cover an area a bit larger than the size of Texas. So my PhD research is addressing the issue that we have, that we can only physically work on a limited number of glaciers around the world because it's logistically difficult, it's expensive. So how do we look at a larger area of glaciers? So our study is seen here in the Canadian portion of the Columbia River Basin, a river basin that's shared between the United States and Canada. And so we have a series of glaciers shown on the left that we're studying, both using traditional mass balance methods, as I indicated before, but we're also using remote sensing to try to get at mass balance that can allow us to look over larger areas. To do so, we use LiDAR equipment, which is essentially a laser sensor seen there on the right, mounted on the bottom of an aircraft. And we fly that aircraft over our study sites, and we're able to take elevation measurements using that and essentially produce a 3D map of the glacier surface. And we're collecting about 1 or 2 measurements per square meter over the glacier surface. So it's a pretty detailed analysis, and this is the kind of product we're able to get from that laser scanner. So this is essentially a 3D map of the toe or the terminus of the Conrad Glacier. So just a small view of the glacier, the lowest portion of it, flowing from the bottom of the page to the top right of the page. And this is 2014, and the next is 2016. So you can see the level of detail that we're able to pick out. You can see the movement of some of the crevasses, but you can also see the glacier not only retreating, but also visibly thinning between these two images as the glacier retreated about 50 to 75 meters, depending on where you were looking over those 2 years. So if we have those type of products, these 3D maps essentially, as Summer mentioned, we can take the difference between two of them. So we're taking these maps at the end of every winter season and at the end of every summer season. So we're able to get something like this, which is a height elevation change map from which we can derive mass change. So we essentially just took 2 3D maps. We have one from September 2015, one from September 2016. The difference between those two is what you see here. This is the Kokanee Glacier in southern British Columbia, and it's flowing from the bottom of the page to the top of the page. The Kokanee Glacier actually gained a small amount of mass in this year, no way offsetting its long-term losses, but you can see the toe of the glacier lost quite a bit of thickness, and the rest of the glacier was a bit neutral or very high in the glacier, slightly positive year. Our results thus far suggest a very good agreement between between both our laser measurements or our LiDAR measurements and our observational measurements. And so those are shown here. If I can draw your attention to the farthest left, that's the Kokanee Glacier again. And you see in the light blue, we have the laser estimate of mass balance for the winter, and the dark blue, we have the observational estimate of mass balance. And likewise for summer mass balance, shown in light red and dark red, respectively. When it comes to the green, if you think back to our first slide, we had accumulation plus melt equals mass balance. So that's simply adding those two columns there, the winter and summer, for each measurement, and then comparing that for annual mass balance. So in conclusion, we really do need a greater coverage of glacier mass balance studies. The reason we do is because glacier mass balance studies are key for being able to understand glacier response to weather and climate. And a greater coverage would particularly allow us to be able to talk about trends across specific regions. As you saw from that original map with about 100 glacier sites, we really only have 1 or 2 sites per region at best. So that's not going to allow you to talk about regional variability or responses to particular things like La Nina or El Nino, just about are we retreating, are we advancing, and we know we're retreating. It's also important that we measure both the summer and winter components because that's critical for water resources. Annual mass balance can tell us how much a glacier is shrinking, but if we want to know how much water it's contributing downstream, we need to know how much snow fell in the winter and then how much melt occurred over the summer. Thank you.
Thank you. Are there any questions from reporters in the room? As a reminder, please state your name and affiliation before asking a question. Just raise your hand. I think we have some questions on the chat.
She wants to know, this is a question for Gerard. What percentage of the world's glaciers does the 227 being monitored represent? And on average, what was the retreat in terms of feet, height, and volume, or other measurement? Thanks.
It's every single one that the World Glacier Monitoring Service has a record of that spans the 20th century. So you want to try and get a record that's as long as possible so you have as much of the industrial era as you can. As a fraction of all the world's glaciers, it's a small fraction because, as Ben showed, there are something like 200,000 glaciers around the world. The average retreat of those 227 is a number that I have in my head, and it was 1.5 kilometers.
Thank you. And we have another question from the chat from Seth Bornstein from the AP. He says, forgive me, I was late and distracted. Is it possible one of you can summarize the 2016 mass balance measurements and the raw numbers, and what can they say about acceleration and this year especially?
Globally?
Seth, did you hear that they wanted to know globally?
It normally takes the WGMS a couple of years to get all of the data in and to quality control it and to produce a flux, and that'll only be for a subset of the monitored glaciers. I don't think the technology exists to provide a global number yet.
No, I mean, we know that 2016 was another mass loss year, but I don't think the magnitude is known yet because most studies haven't yet reported. I mean, our specific area of the Columbia Basin was only a slightly mass loss, but that's just one region.
He said yes, globally.
I don't think that kind of information is available until Ben graduates and gets millions of dollars of research funding.
Okay, are there any other questions from reporters in the room? And are there any other questions on the chat? Oh, I think someone is typing a message, so just hold on one second.
Irene asks, 1.5 kilometers in height, width, for Gerard?
Length.
Length.
And there's a big distribution about that. So some of those are tidewater glaciers, which have gone back. I think the record is 24 kilometers. And then there are other sort of postcard alpine glaciers that would have retreated less than a kilometer.
And she wants to know, where are these 227 glaciers?
They're all over the world. They're primarily distributed in Europe, so the Alps, Scandinavia, North America are dense concentrations of those records. A lot of records from the old Soviet Union, but widely distributed over the glaciarized regions of the Earth.
Okay, and then Seth wants to know, is it fair to say the pace is accelerating?
I don't think we know that. I think you would look at individual glaciers and you might get a different story from each of them. I'm trying to think of images in my head I have of these time series. Yeah, I wouldn't want to say one way. Ben, do you have?
Yeah, it's hard. I mean, area change and mass loss are two different things because glaciers respond more complexly in terms of shrinking an area. The rate of mass loss is accelerating. But as Gerard said, the rate of actual retreat, that depends on more things because a glacier can thin in place and not necessarily shrink in size.
Okay, there was a clarification as Seth said the pace of loss. Is it fair to say that that pace of loss is accelerating?
That's a second order term, isn't it? That's that's an accelerator. I think I don't think we have a good answer. I don't think there won't be a general answer to that kind of question. It's going to be very much dependent on individual glaciers. And as Ben says, you need to be careful about what you're talking about. Are you talking about length? Are you talking about area? Are you talking about mass? Are you talking about thickness? And a more precise answer might be given for a more precise question without being rude. And the answer is going to be glacier dependent.
Okay.
Good morning. Good morning. Mike Karlowitz from the NASA Earth Observatory. This is for summer. Just wanted to both summarize and ask a question. If I heard you right, or read your, if I understood you correctly, what you were seeing in terms of river flow is that in the short run, at least 2 out of the 3 river basins there would be a short-term gain but a long-term loss, and across all 3 there's a long-term loss. This is asking you to speculate, but going past 2100, I mean, you can look at this and say, well, you know, there's more or less snow and whatever, but that's since the water's coming from the ice, in the long term, is that going to be a water issue? This is a limited resource. The ice is the stored water.
Yeah, so the background question that then is just how much do these glaciers contribute to that river flow, right? Because you still have monsoonal rains coming in that feed these rivers. There's snowpack that's seasonal and feed these rivers, and then you have the long-term glacier storage that feed these rivers. So in terms of the glacier contribution long-term, yeah, that's going to have a short-term decrease, short-term increase, long-term decrease that will continue beyond the 21st century.
Has anyone estimated what the ice contribution is to those flows, or is that still at?
It's still a live question. People are doing those estimates, but the range of reported numbers is huge. But right now, one of the things that's becoming more and more of a consensus is the watershed where the glaciers are, we think, truly a sizable fraction of the water is in the Indus. But it also depends on time of year, right? So during the peak monsoon season, the contribution of these glaciers is pitiful, but during the dry season, they become really important because it's the only source of water during those months between the end of the monsoon and the spring snowpack melt, right? So it's, you can talk about it yearly, but you can also talk about those seasonal contributions. And the seasonal ones are where glaciers are going to matter the most, is anywhere where it's dry, and during parts of the season where it's dry, then the glacier contribution increases dramatically. And that's where those changes are going to be really important.
Are there any other questions in the room?
Hi there, Jennifer Lehman from the California Academy of Sciences. Just a quick clarifying question for you, Ben. You mentioned that you might have mentioned that all of the glaciers in the world, they take up a space about the size of Texas. Is that what you said? Did I hear that correctly?
Yeah, the Randolph Glacier Inventory. So these are
okay.
the Randolph Glacier Inventory surveyed counted the number of glaciers around the world, and yeah, it was a little under 200,000, and it was an area a little bigger than the size of Texas. That's outside of the ice sheets, like the Greenland ice sheet and the Antarctic ice sheet.
Are there any other questions in the room? Are there any other questions on the chat? Okay, thank you very much. That concludes our press conference. Next up at 9 o'clock, how animals will fare in a changing climate. Thank you.